Up till now, we have studied infinite transmission line, and in the case of infinite transmission line, in the general case for lossy transmission line, we said that the voltage at any point z would equal V naught plus multiplied by e to the power minus gamma z plus V naught minus multiplied by e to the power plus gamma z. And we said that the first term represents the forward propagating uh, function, and the second term would be the backward propagating function. And here V naught plus is the complex amplitude of the voltage propagating in positive z direction, and this complex amplitude has amplitude and phase. And similarly, V naught minus is the amplitude of the voltage wave propagating in negative z direction. The question now, what will be the situation if this transmission line is finite and terminated by a load resistance Z load at Z equals 0? So in this case, at Z equals 0, the potential would be V naught plus multiplied by e to the power minus 0, which is unity, plus V naught minus multiplied by e to the power 0, which is also unity. So the total voltage at the load in this case would equal the magnitude of the forward propagating voltage plus the amplitude of the backward propagating voltage would be V naught plus V naught minus. So the voltage V plus at 0, it would be V naught plus, and the voltage V minus of backward propagating would be V naught minus. If we are assuming to find out the voltage at any point of such terminated transmission line, so assuming that the voltage at Z equals Z naught, it would be the voltage due to the forward propagating function would be V naught plus e to the power minus gamma Z naught, and the voltage due to the backward propagating function would be V naught minus e to the power gamma Z naught. So in terms of the voltage at Z naught, we can say that the amplitude of the forward propagating wave function V naught plus equal the voltage of the forward propagating function at Z naught multiplied by e to the power plus gamma z, and the amplitude of the backward propagating function V naught minus, it would be the voltage, the backward propagating function V naught at Z naught minus multiplied by e to the power minus gamma Z naught. Now, in terms of the forward voltage at Z naught and the backward voltage at Z naught, we can say that the voltage at the load would be, or the voltage at any point V at point Z would equal V naught plus, which equal V plus at Z naught e to the power gamma Z naught multiplied by e to the power minus gamma Z. So it would be V plus Z naught multiplied by e to the power minus gamma Z minus Z naught. On the other hand, the backward propagating function would be V naught minus, which can be replaced by V minus at Z naught multiplied by e to the power minus gamma Z, and this would be multiplied by e to the power gamma Z, positive gamma Z. So it would be the voltage of the backward propagating function at Z naught, V minus Z naught, multiplied by e to the power gamma Z minus Z naught. So in this case, we say that the voltage at any point Z can be determined in terms of the voltage at any point Z naught in this way. So this simply change of reference from z equals 0 to z equal z naught. And if we going to return back to z equals 0, so at z equals 0, this would be v at 0, which is v naught plus, and v minus at 0, which is v naught minus. Now, at a distance z equal minus d, we can say that the voltage at z equal minus d would be v naught plus multiplied by e to the power minus gamma z, and we are going to replace z by minus d. So minus minus would be positive, so v naught plus e to the power gamma d plus v naught minus e to the power plus gamma z, and z in this case is minus d, so it would be e to the power minus gamma d. So this is the voltage at a distance d from the load, such that the load is located at z equals 0 and the observation point is located at z equal minus d. On the other hand, if we are talking in terms of the current actually I as a function of z equal v naught plus over z naught e to the power minus gamma z minus v naught minus over z naught e to the power gamma z. We are going to replace z by minus d, so the current at z equal minus d would be v naught plus over z naught e to the power gamma d minus v naught minus over z naught e to the power minus gamma d. Here e to the power gamma d is actually e to the power minus gamma z, and z is minus d, so it is e to the power gamma d. And here e to the power minus gamma d is actually e to the power gamma z, and z is minus d, so this is e to the power minus gamma d. So this is the voltage at the distance d from the load, and this is the current at the distance d from the load. Now, if we divide this voltage by this current, we obtain the input impedance at a distance z equal minus d. So, in this case, before going to the input impedance, we are going to simplify this notation as follows. The voltage at z equal minus d was v naught plus e to the power gamma d plus v naught minus e to the power minus gamma d. We are going to define v naught minus over v naught plus as the reflection coefficient of the load, gamma load. So we are going to define v naught minus over v naught plus as gamma load. So by taking v naught plus as a common factor, v naught plus e to the power gamma d as a common factor, so the remaining factor here will be 1 plus v naught minus over v naught plus multiplied by e to the power minus 2 gamma d. This was e to the power minus gamma, and I have taken as a common factor e to the power gamma, so I divided by another e to the power gamma, so this is e to the power minus 2 gamma d. Okay, and v naught minus over v naught plus will be replaced by gamma load. So effectively the voltage at a distance minus d, z equal minus d, equal the forward propagating voltage v naught plus e to the power gamma d multiplied by 1 plus the reflection coefficient gamma load multiplied by e to the power minus 2 gamma d. In a similar way, we can say that the current at z equal minus d would be v naught plus over z naught multiplied by e to the power gamma d, which is the forward propagating current, multiplied by 1 minus gamma load multiplied by e to the power minus 2 gamma d. Now, by dividing the voltage at distance z equal minus d over the current at the same distance, we can obtain the input impedance at z equal minus d. So the input impedance z at minus d would be the voltage over the current at this point. So the voltage over the current at this point would be this function over this function. In this case, this V naught plus will be eliminated with this V naught plus. This e to the power gamma will be eliminated with e to the power gamma d. And this z naught would be the denominator of the denominator, so it would be in the numerator. So it would be z naught multiplied by 1 plus gamma L e to the power minus gamma d over 1 minus gamma L multiplied by e to the power minus 2 gamma d. Or in other words, if we are going to define gamma at minus d is gamma L multiplied by e to the power minus 2 gamma d, so it would be 1 plus gamma at z equal minus d over 1 minus gamma at z equal minus d. Okay? Alright. So this is the input impedance after a distance z equal d from the load. It can be noted here that this input impedance is function of the distance. So the problem now, it is not a short circuit, it is not a wire. Effectively, it is a transmission line, and the length of the transmission line controls the input impedance in this case. Okay, if we are going to assume that the distance d equals 0, so effectively the input impedance at z equals 0 is the load, because we didn't move from the load itself. So z at distance d equals 0, it would be z load. And by applying e to the power gamma d, where d is 0, it would be unity. So z naught multiplied by 1 plus gamma load over 1 minus gamma load would be the value of z load. So by arranging this equation, we can obtain gamma load in terms of z load and z naught as gamma load would equal z load minus z naught over z load over plus z naught. So in this case, the value of the reflected waves over the value of the incident wave, or the value of the backward propagating wave over the value of the forward propagating wave, which is the reflection coefficient, would equal the difference between the load impedance and the characteristic impedance over the load impedance plus the characteristic impedance. On the other hand, at any point at d greater than 0, the reflection coefficient gamma at minus d, it would be the reflected field or the backward propagating wave at distance minus d over the incident or the forward propagating wave at distance minus d. In this case, it would be the value of gamma L multiplied by e to the power minus 2 gamma d. Because effectively, when I have moved a distance d, the forward propagating function has been delayed by e to the power minus gamma d, and the backward propagating function has been delayed by e to the power plus gamma d. So the ratio between them, it would be e to the power minus 2 gamma d. But effectively, the reflection coefficient gamma L is the same. Okay, so at a distance z equal, or the impedance z at a distance equal minus d, we have proved that it is z naught multiplied by 1 plus gamma at z equal minus d over 1 minus gamma of z equal minus d. Or in other words, it is z naught multiplied by 1 plus gamma e to the power minus 2 gamma d over 1 minus gamma e to the power minus 2 gamma d, where gamma L is the reflection coefficient at the load, and the reflection coefficient at the load is given by Z load minus Z naught over Z load plus Z naught. Okay, so we are going to replace this gamma L by the ratio Z load minus Z naught over Z load plus Z naught. So the input impedance at a distance d from the load would be Z naught multiplied by 1 plus Z load minus Z naught over Z load plus Z naught multiplied by e to the power minus 2 gamma d over 1 minus Z load minus Z naught over Z load plus Z naught multiplied by e to the power minus 2 gamma d. We are going to simplify this equation. Effectively, this equation is quite sufficient, but we are going to simplify it. So, by multiplying both the numerator and denominator by Z load plus Z naught, so it would be Z naught multiplied by Z load plus Z naught plus Z load minus Z naught e to the power minus 2 gamma d over the same equation but with negative sign. Okay. Now by multiplying the numerator and denominator by e to the power gamma d, so it would be Z load plus Z naught e to the power gamma d plus Z load minus Z naught multiplied by e to the power minus gamma d. And the same here, but with negative sign. Okay. Effectively, in this case, we can take the terms which has Z load together. So this would be Z load multiplied by e to the power gamma d plus e to the power minus gamma d. E to the power x plus e to the power minus x is 2 cosine x. So effectively, this would be 2 cosine gamma d multiplied by zf. In a similar way, z naught e to the power gamma d minus z naught e to the power minus gamma d, we can take z naught as a common factor. So it would be e to the power gamma d minus e to the power minus gamma d. This it would be 2 sin gamma d. And because we have factor 2 in the numerator and a similar factor 2 in the denominator, so we can show that the input impedance at a distance d from the load would equal z naught multiplied by z load cosine gamma d plus z naught sin gamma d over z naught cosine gamma d or plus z load sin gamma d. We can divide both the numerator and the denominator by cosine gamma d. So it would be z load plus z naught tan gamma d over z naught plus z load tan gamma d. So the input impedance at a distance d from the load would be z naught multiplied by z load plus z naught tan gamma d over z naught plus z load tan gamma d. If you wish to memorize this equation, it is very simple. This is the input impedance. We are going to start with the characteristic impedance of the transmission line, so Z naught. Then the second term would be the load impedance, Z load, plus we start from Z naught to Z load, plus Z naught tan gamma d. This is the denominator. The denominator is effectively the reverse of the numerator. So the denominator, instead of Z load, would be Z naught, and instead of Z naught would be Z load times gamma d. And effectively, this is a very important equation in microwave engineering. So you should memorize it. Alright? Okay. So In conclusion, the summary of lossy terminated transmission line: if we have a lossy transmission line and this lossy transmission line is terminated by a load impedance Z load, and this load is located at Z equals 0, so the reflection coefficient along at the load, gamma load, the reflection coefficient at the load would be Z load minus Z naught over Z load plus Z naught, and the input impedance at a distance d from the load, it would be Z naught multiplied by Z load plus Z naught tanh gamma d over Z naught plus Z load tanh gamma d, where gamma is the complex propagation constant of the lossy transmission line, which equal the square root of R plus J omega L multiplied by G plus J omega C, and the propagation or the guided wavelength in this case, it would be 2 pi over beta, where beta is the imaginary part of the complex reflection coefficient or complex propagation constant, and the phase velocity would be omega over t. This is actually the summary for lossy terminated transmission line. Okay. The question now, what about the power? Effectively, the power in terms of the voltage and current, it is determined as half the real value of V multiplied by the conjugate of the current. And the voltage at any point along the transmission line is determined as V naught plus multiplied by 1 plus the reflection coefficient gamma. So V at any point is V naught plus E multiplied by minus gamma Z, the forward propagating function. This multiplied by 1 plus gamma load, the reflection coefficient at the load, multiplied by e to the power 2 gamma Z. And the current at any point along the transmission line, it would be V naught plus over Z naught multiplied by e to the power minus gamma Z, which is the forward propagating current, multiplied by 1 minus gamma L e to the power 2 gamma Z. And gamma is alpha plus J beta. So we are going to replace each gamma by alpha plus J beta. And after replacing gamma by alpha plus J beta, we are going to take the conjugate of the current. So the conjugate of the current in this case, it would be V naught plus conjugate over Z naught conjugate multiplied by e to the power minus gamma conjugate multiplied by 1 minus gamma L conjugate multiplied by e to the power 2 gamma conjugate Z. So everything in the I would be conjugate. By taking the conjugate of the current and multiplying it by the voltage at any point Z, we can obtain V multiplied by I conjugate is V naught plus squared as a magnitude over Z naught conjugate multiplied by e to the power minus 2 alpha Z, one from this exponential term and the other from the other exponential term, multiplied by 1 plus gamma L e to the power 2 gamma Z, the first term, multiplied by 1 minus gamma L conjugate, multiplied by e to the power 2 gamma conjugate Z. Now, by performing the multiplication of these two brackets, we can find out 1 multiplied by 1, gamma L multiplied by e to the power 2 gamma conjugate, multiplied by gamma conjugate, multiplied by e to the power 2 gamma conjugate Z. Effectively, it is gamma L squared multiplied by e to the power 4 alpha Z. And the remaining part due to the imaginary part would be removed in the conjugate. Okay? So this is a multiplication, this term by this term. Now the remaining part is this term and this term. So this term, it would be gamma L e to the power gamma z minus gamma L conjugate e to the power 2 gamma conjugate z. So these are the remaining two terms of the multiplication of these two brackets. So the first two terms of the multiplication is this term, and effectively in this case everything is real except z0 conjugate. So we can say that the real part in this case is half v0 square e to the power minus 2 alpha z multiplied by this bracket, okay, real 1 over z conjugate. And effectively the characteristic impedance is usually near to be real. For the case of lossless transmission line, it is pure real. For lossless transmission line, we are going to assume that z0 is nearly the real value. So in this case, the real 1 over z conjugate is nearly 1 over z0, or the real part of z0. Now the remaining part is the other two terms of this multiplication multiplied by this term, and it should be noted here, this number or this value is the conjugate of this value. And if we have two values, z minus z conjugate, and assuming that z is x plus jy, so x plus jy minus x plus jy conjugate, which is x minus jy. So in this case, this term is pure imaginary. So by taking the real part of this pure imaginary part, it would be 0. So this term actually doesn't contribute to the real value of the power. So the real value of the power is basically determined by the first bracket only. So the time average power in this case, it would be half v0 plus squared over z0 e to the power minus 2 alpha z multiplied by 1 minus gamma load squared e to the power 4 alpha z. It means that we have forward propagating power and backward propagating power. And if alpha equals 0, so in this case, the forward propagating power is effectively the voltage squared over 2z0, and the backward propagating power, it would be the reflection coefficient squared multiplied by the incident power. This is effectively the time average power flow in lossy terminated transmission line.